Okay, so welcome everyone to the, spring 2024 mini course. And today we'll have Julie Bergner, who will be telling us about an introduction to 1 and 2 Siegel sets and spaces.
Okay, well, thanks, Sarah, for the introduction, and Guchan and Dan and all the eCHT people for the invitation. Really honored to be invited. So I decided to give a talk on this topic. I've really been thinking a lot about two Siegel objects quite a bit for the last several years, and I think they're really interesting. I think there's a lot more to be done with them, and I think they deserve to be better known. And I'm hoping that this will be an opportunity to kind of spread the message a little bit more with this audience. So today is just going to be a pretty gentle introduction. A lot of what I'm going to say is probably going to be familiar to a lot of people in the audience, but I didn't want to assume. So I'm going to just kind of review some basics about just simplicial sets, simplicial objects, because they're really key to the theory. And then talk about one Siegel object, well, one Siegel sets to start, just the discrete case. Go into two Siegel, talk about some examples, and then go into spaces and 1 and 2 Siegel spaces and more general objects. And then in the subsequent talks, we'll take this in some different directions and look at some of the ways that these can be applied and why people are interested and excited about them. Okay, so just a quick overview. People may be familiar with Siegel things a bit already. It doesn't usually have a 1 in the front unless you're going to go on and talk about 2 Siegel, as I'm going to. So I will go ahead and use the 1. But the idea is that, again, I'm going to keep everything sort of discrete at this moment and just talk about 1 Siegel sets. And these are things, well, they really should just be categories, but I'm going to say they're things that behave like categories in that they have objects. So I'll denote those with dots. They have morphisms. So we think of those as arrows between dots. We have unique composition. So if we have 2 morphisms that sort of follow one another, then there's a unique way to compose them. And this composition is associative. So heuristically, that's the kind of structure that this is supposed to encode. 2 Siegel is going to be something a little bit weaker. So we're still going to have objects and morphisms, but in this case, composition may or may not exist. And even if it does exist, it may not be unique. So when we have a little configuration of morphisms like this, sort of a question mark, whether we can fill that in. It also could be that there could be sort of multiple ways to fill it in. But it is still associative. You may have some questions about what that means if composition is so up in the air, but we'll go into more detail about what that is. But this is just sort of the idea. Okay, so our goal today is just to introduce and define these in a rigorous way. And again, we'll start with sets and then we'll move on to spaces after that and just give several examples. So you can get a sense that this isn't just an abstract definition, but they're actually, this is actually useful. Okay, so to begin, again, we're just going to have a really quick crash course in simplicial sets. If you don't know what these are, then you're going to have a hard time with the rest of the topic. So we first have the category delta. So this has objects, finite ordered sets. So we'll write these as bracket n. So these are just the and bracket n is the set with n plus 1 elements that we write 0 up to n with your usual ordering. And this is for every n at least 0, and then the morphisms are order preserving. So these sort of assemble into a category. So for example, there are 2 order preserving maps from 0 to 1, either 0 goes to 0 or 0 goes to 1. There's only 1 order preserving map from 1 to 0. And then, well, we have more of them going from 1 to 2. I'm not even writing all of them. I'm not writing the ones that collapse everything, but you could send, say, 0 to 0 and 1 to 1. You could send 0 to 0 and 1 to 2. Or yeah, 0, which one did I miss? 0 to 1 and 1 to 2. And then 2, you can collapse 0 and 1 down to 0, and then anyway, and so forth. Anyway, so these assemble into a category, and then we're actually going to just take the opposite category. Delta op, and this just has the same objects, and we just reverse the direction of all the arrows. And so now a simplicial set is a functor from this category delta op into the category of sets. So what that means is every one of these finite ordered sets gets sent to a set. So column, say K0, K1, and so forth. And then we have maps going between them as indicated by the category delta op. So these sort of downgoing arrows are what are called face maps. And then the upward ones are called degeneracy maps. And if these are not familiar to you, but you know about simplicial complexes, what's happening here is just you're picking out the face. You're thinking of the elements of Kn as being an n simplex, and then you're just picking off the n-1 dimensional faces. So I'll even write a little bit of that down. So idea is that Kn is the set of n simplices, and so we have, say, a 2 simplex, and part of what this structure, I mean, sort of encoded by these maps, we can order the vertices, and then we actually can kind of think of them this way, as arrows and then this is filled in. So this is a 2 simplex. We expect to have 3 face maps, and we just say, all right, well, we have what we call D0, and you just take the face that you get by omitting the 0 vertex. So we're just left with this face that goes from 1 to 2. Similarly, D1, we just leave off the vertex 1, and we're left with the arrow from 0 to 2. And finally, D2, we leave off the 2 vertex, and we're left with the face, sorry, that's a 1. Left with the face from 0 to 1. Now, the degeneracy maps are what are new. We don't have an analog in simplicial complexes, but they're going from a simplex of a lower dimension to one of a higher dimension. So, and that's exactly what their purpose is. So they allow us so we think of a simplex as one of a higher dimension. And so, for example, if I have a 1 simplex, say from 0 to 1, now 1 simplices, I should have 2 degeneracy maps. I should be able to think of it as a 2 simplex in 2 different ways. And we're thinking of as sort of doubling up. So sort of I tend to think of it as sort of a very short face. So you'd say, well, I sort of double up 0 and I get a little skinny, think of it as sort of a skinny 2 simplex. And then S1, the other one, I think of sort of doubling up the 1 over here. So I sort of have 2 simplex like that. All right. And then, I mean, kind of why these were originally developed was to model topological spaces in a combinatorial way. And I'm not going to talk about this in detail, but simplicial sets can be geometrically realized to topological spaces. And there's an official formula for that, but you can think of it sort of just as I've depicted them. I've been kind of already doing that by drawing them as literal line segments and triangles and things. I mean, as in the definition, they're just elements of a set, but we really think of them in the topological way. Okay, so a couple of important examples. So one is what I'll write as delta bracket n, the n simplex. And so this is the simplicial set whose k simplices are given by the morphisms in delta from k to n. So it just says, well, I'm just mapping into a fixed n. So n is fixed, k is varying. So this is the representable simplicial set. So it's a representable functor from delta off into sets just by mapping into a fixed n. And this does exactly what you want under geometric realization. This geometrically realizes to the topological n simplex that you know and love, which I'll write as delta over n. So justifying some sense of pictures, but okay. And then, so one more example. So if I have a group, so say G, then we can take its nerve. So this is the simplicial set where I take a single 0 simplex, so it's just a point. And then I put G, here, G is just a discrete group here, no extra structure here. So I just think of G as a set, put it in dimension 1, and then in dimension 2, as it's two simplices, I put G cross G, and then keep going. So have product of n copies of G with itself at level n. And yeah, I mean, the maps here, I mean, these maps are just what they have to be, just down, I mean, you can think of this as the trivial group here, or just think of it as a point. What's happening here, the face maps, well, two of them are just the projections to the two copies of G, but then the middle one is where you use the multiplication in G to get that middle face map D1. And then the degeneracy maps are just the inclusions, where you just take, you know, little g goes to either G comma identity or identity comma G. All right, and now its geometric realization. So I didn't give, so this is nerve of G. So if I take the geometric realization of the nerve of G, this is one model for the classifying space, BG. Or if you like, this is an Eilenberg McLean space of type G1. Now, there wasn't really anything special about this being a group. We didn't really use the group structure. So a monoid is perfectly good. And in fact, we can add more objects. So we can do this for any small category. So we take C. So its nerve is just slightly more complicated. So now we put all the objects of C as the zero simplices. And then as the one simplices, we put all the morphisms. Okay, and now our two face maps are just the source and the target, and the degeneracy, and then the degeneracy is the identity morphism on an object. And then for our two simplices, we take pairs of composable morphisms. So unlike in the case of a group, we can't just take a product, we need to take morphisms that can compose with each other. And this looks like a picture we saw earlier. So we have two arrows, the source of one is the target of the other. And then, well, if this is a category, then we know that there's a unique way to fill this in and get a two simplex. So this is starting to look a bit like our description of one Siegel things at the beginning. But maybe this is a good place to stop, just if there's any questions.
I was just wondering what the KG, 1 was. Maybe I missed that.
Oh, it's just it's a space that has, so KG1 is a space whose fundamental group is G and all its other homotopy groups are trivial. So
Okay,
it's not important, particularly for the talk. If people have seen that, then it's if it's not familiar, it's okay.
Okay, thank you.
Yeah. Okay. All right. So this leads to our formal definition of what a one Siegel set is. Okay, so a one Siegel set is a simplicial set. Okay. Such that if I take Kn, the set of n simplices, that this looks like an iterated pullback of a bunch of copies of K1 glued along K0. So there should be n of these. And I want this isomorphism to hold, well, I'll say for every n at least 2. It's going to hold when n equals 1 or 0, sort of vacuously. So those are the interesting ones. Now, and if I really want to make this a complete definition, I need to tell you what this pullback is. And the idea is that I want to think of this as a generalization of what I have here. I want it to be a string of n composable morphisms, and I just want to be able to build that up to an n simplex. So these maps come from, well, I can take this. So if I have this string of n composable morphisms, I mean, this is a simplicial set. I can think of it as just taking the one simplex and then just taking a push out of a bunch of one simplices that agree along 0 simplices. And well, again, it's as indicated. So you want well, I don't want to say sources and targets. This isn't a category, it's a simplicial set, but you sort of want the 0 face of this arrow this arrow that gives you this object here to be the one face of this arrow, and so on and so forth. So it looks like a string of composable arrows. All right, I'm gonna follow reasonably standard notation. It's sometimes called a spine, or sometimes called G of n. And as a simplicial set, this includes into the n simplex. So for example, when n equals 2, these are some of the pictures I've already drawn. So you have your sort of pair of composable arrows, and this includes into a 2 simplex. And maybe I'll put some color here. So it's just this inclusion here. And then you can imagine having these for higher dimensional ones as well. Okay, but what does that have to do if what does that have to do with these maps for an arbitrary simplicial set K? Well, what I can do is I can map, these are perfectly good simplicial sets, I can map them into a fixed simplicial set K. So and mapping into something fixed is contravariant, so we get a map from Hom from delta n into K to Hom from Gn into K. And well, I said this delta n was representable functor, so a consequence of the Yoneda lemma is this is just isomorphic to the set of K simplices. So this is just Kn right here. And then if you think about, okay, what happens when I map this Gn into K? Well, that's going to pick out a string of one simplices. So this is going to look like the right-hand side over here. So this looks like this pullback. When I map this thing into K, the push out that we had up here turns into a pullback. And so this is this map. And these are often called Siegel or one Siegel maps. So these maps always exist for any simplicial set. The question is, when are they isomorphisms? And that's the condition that we're saying, well, when these maps are all isomorphisms, that's what we call a one Siegel set. And in fact, these end up being the same thing. So a simplicial set is a one Siegel set if and only if, well, at least up to isomorphism, It's the nerve of a category. Now, so if you have such a K over here, then you say, well, so K0 becomes your objects, and K1 will give the morphisms. But you might wonder, well, what about associativity? Composition and then associativity. Composition's the main one I want to talk about. So if you have, well, in any simplicial set, you have maps. So this is D0, D2, your two, the two face maps. And then I have D1 over here, that's going to go to K1. And if this is a one Siegel set, then this map is going to be an isomorphism. And so I can just take its inverse and then compose with D1, and that's going to give me the composition in my category. So, okay. And then you can check that part of this structure. You've got to go up to K3, but you can check that associativity is going to hold. Okay, so that's one Siegel. So this one Siegel is basically just categories, but just rephrased, framed in the context of simplicial sets. Okay, so now what about two Siegel sets? And so the definition that I'm going to give you is the definition due to Dickerhoff and Kapranov. These were also defined, and I guess the way I've defined them, these would be called discrete decomposition spaces. And this was due to Galvez, Carrillo, Koch, and Tonks. So this is one of those cases where kind of the same notion came up at really right about the same time from two different perspectives. So I'm going to give you the definition of Dickerhoff and Kapranov. I'm going to take their approach. The definition the others gave is just a little bit different, but they end up being equivalent to each other. Maybe at some point I'll come back and say a little bit about their point of view, depending on how things go, but not today. All right. So what is going to be true about this? Hopefully by the description I gave you already, you conclude in this doesn't actually mean higher categorical. It doesn't mean two categorical. It just means something weaker. Well, if we think of GN, this thing we use to define the simplicial set we use to define one Siegel, we can think of that as triangulating a line segment. We're sort of saying, okay, chop up I've got some directionality, but I'm sort of chopping up a line into n pieces. And that's a one-dimensional thing. So now I'm going to use a two-dimensional triangulation to generalize this. And we're going to triangulate regular polygons. All right, so while we're going to assume they're regular, we're also going to assume sort of with cyclically labeled vertices. Just have a convention. So our first non-trivial example is when we have a square. So again, I want to think of this as a simplicial, what I'm going to build here is going to be a simplicial set. The cyclically label thing is, well, so I'm going to start with 0. In this case, I label up to 3. And then I'm thinking, all right, there's going to be a simplicial set. I'm going to put in the arrows just so you know what the sort of face map structure is. And in this case, I have 2 choices. Just convention here, we're not, in general, when people talk about triangulations, you can sometimes add new vertices to get, fancier triangulations. Here, we're not going to do that. We're just going to use the vertices that we have. We're not going to add any new ones. So we can either add an edge from 0 to 2, or we can put in the other diagonal instead. So we can add in this edge from 1 to 3 instead. And now, well, we can put in the middle, now just as these things included into higher simplices, in this case, these are both giving you a pair of faces of a 3 simplex. So these both include here. So let me call these, I'm going to call this T1 for the first triangulation, this T2 for the second triangulation. And now we can do the same thing here that we did with our map from Gn to delta n. We can just map each of these into a fixed simplicial set K. And if we do that, so we map T1 into K, and we have delta 3, and then we have T2. And now all the maps go the other way around because we're mapping into K. And if you notice, well, if I map T1, that's going to pick out two simplices that agree along a common one-dimensional face. So this is going to look like a pullback of 2 K2s along a K1. Now, if I don't, this is also going to look like mapping two simplices that agree along a 1 simplex, but the structure is different. The maps are different. And in fact, this map is going to be D1, D3. So this is where, so if I leave off the one vertex, the face opposite, I get 0, 2, 3. That's this triangle here. And if I leave off the third one, the face opposite that is 0, 1, 2. And those are exactly the 2 triangles that I get here. And similarly over here, this is D0 and D2. Okay. And so, so this is the example we get when n equals 3, and we use a foregone, but we can generalize this, and we can do the same kind of thing for polygons with more sides. Okay, so now we're ready for the definition. So a 2-Siegel set K is a simplicial set such that for every excuse me, for every n at least 3, and every triangulation of a cyclically labeled regular n+1 gon by vertices. The by vertices, again, just means triangulation by vertices. I'm not adding any more vertices. Then the induced map so this will induce a map from Kn to a bunch of copies of K2 along K1. Can check that there will be n minus 1 copies of K2, and that this is an isomorphism. And just as we did with one Siegel, these are called the two Siegel maps. All right, now at the beginning of the talk, I claimed that these should have a particular structure. So we should check that this really does have that. So we still have objects. So given by the set K0 and morphisms K1, we really just have those coming from the structure of a simplicial set. But now if we try to do composition like we did before, so remember we said, all right, well, take a composable pair of one simplices, so we think should have a composite, and then we map this D0, D2, and then we have D1. But now we don't know anything about this map anymore. This was a one Siegel map. We don't know anything about it if we're just two Siegel. And so, well, we don't know. So the best we can do is to say, well, okay, take an element here, take its pre-image, if it exists. I mean, it could be empty. Take the pre-image in K2 and then push it over to K1 via this first base map. So this could be empty if this map is not surjective, or it could have, the preimage could have multiple elements if this map is not injective. Okay, but it is still associative. And the best way to see that, I think, is just by going back and looking at this picture. So if you think of this, sort of the boundary here, well, going from 0 to 1 and 1 to 2 and 2 to 3, that's like a string of three, what we'd like to be composable arrows. And if we have a configuration like this says, well, there is a composite of these two arrows. I can compose them. And it says, whatever that composite is, I can compose it with this arrow from 2 to 3 to get this map here. And then having this configuration over here is the other way around. It says, well, now I have a composite of this arrow with this one that I can then pre-compose with this arrow. So you can think, if I call these like F, G, and H, then this side over here is sort of like having H composed with the composite of G and F. And this is like saying I have H composed with G, then composed with F. And the fact, if K is 2 Siegel, then either of these uniquely determines the 3 simplex. And that says, well, then this arrow 0 to 3, I mean, is the unique value for either of these. So they have to agree. We have to be associative. Okay. Now, the other thing, I guess I didn't say anything about this before. The other thing you need in a category is having identity elements. And what you think of then, say your identity elements, well, this always makes sense, is just as elements, you just take the degeneracy, the degenerate one simplices. So the things that arise as images of degeneracy maps from 0 simplices. But the fact that they behave, well, if you're 1 Siegel, that they behave like identities, that they compose the way you think that they should, well, that's going to follow from the simplicial identities with the 1 Siegel conditions. Here, it was not so clear. And so historically, I mean, Dickerhoff and Kapranov, in their definition, originally imposed a unitality condition. So, identities composed as expected. But it turns out that, well, it ended up being 3 groups, well, 1 group and 2 other individuals all kind of realized at the same time that this was unnecessary. And so they all got together. It's one of these papers that has more authors than pages, I believe. So this is due to Feller, Garner, Bach, Underhill, Proul, and Weber. And that's that all 2 Siegel sets are unital. So this ended up being an unnecessary thing. So we have, yeah.
Sorry, is that a strict unitality or a weak unitality?
In this case, because we're just in the discrete case with 2 Siegel sets, it's strict.
Okay, great.
Yeah, when we get to the homotopy version of things, then everything will be up to homotopy at that point. But
okay,
right now we're still just working with sets and isomorphisms, and so it's strict. Yeah.
perfect. Thanks.
Mm-hmm. Okay. Are there any other examples? I'm sorry, any other questions before I go to examples? I haven't given you any examples yet. Okay, so I want to talk about so 2 examples just to start. We will see more in the days ahead. But the first is just what are called partial monoids. Okay. And as the name suggests, these are things like monoids, but composition sometimes exists and sometimes it doesn't. So partial monoid is a set M. So this is the sort of how to describe that formally. So it's a set M together with some subset, we'll call it M2, of M cross M. And this is called the domain of multiplication. So if you had a monoid, this would be all of M cross M. I can pick any 2 elements of M in any order, and I can multiply them. And this says, well, that might just be a subset. And then there's a rule, we'll call it a dot, an operation. So it's not going to go from all of M cross M, it's just going to go from M2 to M. And well, we want to have this to be somewhat reasonably well behaved. So we say this is going to satisfy. So if I have M times M prime times M double prime is defined. So sort of one side of associativity is defined if and only if the other one is. And they are equal. So again, this is sort of the best you can do with associativity if you don't always have composition. It also has a unit, identity element, such that so 1 comma M and 1 M comma 1 are always required to be in the domain of multiplication for all elements M of M. And the result of multiplying them is the same for both of them, which is M. So this is this unitality condition, a little more explicit than what I said above for this example. Now that's a very algebraic way to define it, but we can interpret it as a simplicial set. Which I will also just call M. So M0 will just be the identity 1, that single object set. M1, the set of 1 simplices, will just be M. And then for the higher MKs, these will be a subset of the k-fold product of M with itself. And so we'll say that a k-tuple, M1 up to MK, in MK is going to be an element of M upper K is going to be in M lower K, such that if I that I can multiply the first I elements together. And then I can pair that with Mi plus 1, and that's going to be in M2. So this is an inductive definition of. So I'm building on, so M lower 2 will be just as we defined it up here, and then we use this definition to make sense of the higher MKs. And then our face maps are given by multiplying adjacent terms. Those are the middle ones, the outer ones, then you just drop terms. And then the degeneracy maps, you just insert an identity. Was there a question, Doug?
Yeah, do you want another condition where you've got, say, M1 comma, then the product of M2 through Mi plus 1? Do you want that to be an M2 as well, in big M2? I mean, is there so in the thing you wrote that you've got the single factor on the right, is there another condition where the single factor is on the left?
I'm thinking that might be unnecessary because of the associativity.
Yeah, I was thinking that you could define MK to just be all of the K tuples for which the product is defined. And that's because of her condition that they're defined if and only if they're defined, then that's just, it doesn't matter how you parenthesize it.
Yeah. So so Doug, I think you could put that condition in, or you could do what Dan just said and sort of you could drop the parenthesizations. I think either of those approaches would work.
So it's unnecessary to state the other condition.
Yeah, well, I like stating this condition because it's emphasizing the associativity. But yeah, I think that's right.
Okay.
Missing an R here, insert, okay. All right, and then you can check that this is 2 Siegel. It seems to match with our intuition. Well, I'm gonna verify one of the conditions. So if I take the map, so here's my, if I have a 3 simplex, again, this is just kind of schematic, and I take that triangulation, I'm gonna do this one, use this one, I'm sorry, no, I'm gonna do the other one. All right, the one that's D0, D2. I'm gonna check this map. So I'm gonna input a 3 simplex, right? This is K3, and I'm gonna output a pair of 2 simplices that share a common face. So if I sorry, this should be like in K, but this is how the schematic picture looks. So if I take D0, that leaves me with the face 1, 2, 3. And if I take D2, that leaves me with the face 0, 3, 1. And then the common face between them is 1, 3.
Sorry, I think that the bottom might be going a bit off the screen.
Oh, I'm sorry. Yes, thank you.
Great. No,
It
thanks.
happens, yeah. Okay, and I mean, it just so happened, I mean, this is the map D1, and this is the map D0, if you're keeping track. And I claim that if I just had the data, if I had the data of just this part here, that would uniquely determine the 3 simplex. So, yeah, so the 3 simplex, so yeah, let me write out. So if I have an element, a 3 simplex of this partial monoid, this looks like a triple. So this is something in M cross M cross M that satisfies these conditions. And then if I apply D0, that's just leaving, sorry, this is a 3. That's going to leave off, it's going to drop the first term. I'm going to be left with M2, M3. If I apply D2, that's going to multiply M2 and M3. And now over here, if I apply D1, that's just gonna, so this is a 2 simplex, applying D1 just multiplies them, and I'm left with M2, M3, but that's exactly what happens if I apply D0 over here, it just leaves off the M1. But if you think about that and you say, all right, if I knew that I had this piece of data mapping down here, and I had this data, I could uniquely recover this 3 simplex right here. So, I mean, knowing that they have to be these maps, just this bit here is going to determine the 3 simplex. And so that's the idea behind checking the 2 Siegel condition. Okay, so I want to do, I think I have time for one more example. Okay, and then so this is a more geometric example. And I'm going to start with the 1 Siegel version. So we have the cobordism 1 Siegel set. It's called the cobordism category 2 cob. And I'm going to write it as a 2 Siegel set, as a simplicial set, rather than as a category. So it's 0 simplices. So these are going to be closed one-dimensional manifolds. So example, just bunches of circles. Then as its morphisms, this is going to be diffeomorphism classes of two-dimensional cobordisms. Right, that's sigma. So e.g. I have, maybe a pair of pants. And I'm taking diffeomorphism classes, so I get some kind of strict composition. And then when I go to higher simplices, then I just sort of have decompositions of these. So again, these are diffeomorphism classes of two-dimensional cobordism sigma decomposed as a composite of K cobordisms sigma 1 up to sigma K. So for example, I might have something that looks like a pair of pants composed with some other cobordism and then some other cobordism here. So I have it, it's one big cobordism, but I sort of think of chopping it up into smaller ones that got glued together. Okay, now in this case, composition is always defined. It's a one Siegel set. But the way we can get something to Siegel is by imposing a genus constraint. So say, so let's say the genus can go no higher than some fixed G, then we can no longer compose everything because we might do a composition that would make the genus go too high. So we get a two Siegel set that I'll write 2 cob upper less than or equal to G. So this is even interesting just when G equals 0. So you could compose a pair of pants in this direction where you just glue the circles. But if you do the other gluing, where you want to glue the two circles together, this would not be allowed because you would create genus. And this is, this apparently comes up in TQFTs and such where, you want to impose conditions like this. So it's again, just another example of where we can find these two Siegel structures in the wild. So I did not actually get to spaces today. We just stayed with the discrete case, but then I will resume and talk a little bit about that on Thursday. So just a couple places that we're going. So to come, I mean, one of the things, well, first of all, two Siegel spaces are more general two Siegel objects in other categories. And then I want to talk about the close relationship with the S-dot construction, which is important in algebraic K-theory. And then I also want to talk about all algebras and how these give a unifying construction of those. And well, we might get to some other things depending on how long those take. Yeah. So so I'll stop there for today.
All right, let's all thank Julie for the first lecture in the mini course.